Okay, ladies and gentlemen, we're coming back to the basics after the excursus to software and the application. And now I'd like to introduce CAN XL, which is the next generation of the CAN protocol series. And we have started this already in 2018, when some engineers from Volkswagen came and said, oh, 64-byte of payload is not sufficient. I personally was a little bit surprised, because we just had introduced it, was not adapted in those days. And then gentlemen came and asked me for the next generation. As you may know, I'm already retired in 5 years, and I thought I can hand over the entire CAN technology to my successor. But now I have the task to make the next generation running. This is the third generation. I will explain a little bit about the development, and then about the physical layer, which has some challenges, and we have and then also the higher layer protocol configuration, which was not capable in the past, but now we can configure the higher layer protocols from the data link layer. And also we'll talk a little bit about the CAN add-on functions, reporting about the first plug test and product availability. So this maybe is some information, just giving you an outlook to the next 5 years, so that you can decide if you want to go this way with me and with others. Just first a short comparison between the 3 different CAN generations. You see CAN Classic or CAN CC, or we abbreviate it now. This, you know, has 8 bytes of data field length. CAN FD has 64 bytes, and now we will have 2048 bytes. This is really a lot. It's even larger than Ethernet is. The priority is in CAN CC and CAN FD, the very same. We're using the 11 or the 29-bit identifier. In CAN XL, we have just 11-bit, because we have separated the function of priority and addressing. In classical CAN and in CAN FD, priority and addressing is using the same field, the 11 or the 29-bit identifier. Now we separate this, and we have an additional 30-bit acceptance field for addressing purposes. What was not available in CAN CC and CAN FD is the service data unit type and virtual network natural CAN network IDs. These are, so to say, configurations that we can run multiple instances on the frame level, and this is quite new functionality, which I'll explain a little bit more in detail. Bit stuffing is what we need to protect the data. And we have a dynamic bit stuffing in CAN CC. This has some drawbacks, and so we have introduced in CAN FD already a fixed bit stuffing in the CRC field, and in CAN XL we have a dynamic only in the arbitration field, and in the entire interface field we have a fixed bit stuffing. So with this we can really achieve a Hamming distance of 6. Hamming distance of 6 means 5 randomly distributed bit errors can be detected by the protocol. And this was not able to do so with CAN CC and CAN FD. Error signaling is always enabled in CAN CC and CAN FD. However, in CAN XL we can switch it off, because some people, in particular those which are in the software business, they want to have this on the network layer level. They don't want to have it in the transport layer level. They don't want to have an error signaling on the data layer. Fast mode is a new bit coding schema, and this is not supported in CAN CC and CAN FD, and this is only available in CAN XL. And there we can reach bit rates up to 20 megabit per second. So this is one of the reasons. And the bitrate ratio is not applicable for NCC because there is only one bitrate. In KNFD we can have a bitrate ratio from high to slow up to 16 times, and in KNXL we can have up to 40 times. So this is a short summary of the features of the three protocols. If we're looking to the possible net rate which we can achieve, we see that we are now able, if you are running very fast with long frames, we can achieve about 14 megabit per second for the net bit rate. And if you are slowing down the bit rate, then you of course have also a lower net bit rate. And in KNFD we can just achieve about 4 plus megabit per second. But where is classical KN? Oh, you can't see it on the slide, I think. It's here. This is the net bit rate. This is 500 kilobit. This is much, much lower than the 14 megabit which we can achieve with KNXL. So this is really a big jump from classical KN to KNXL. The structure of a frame looks like to classical KN and KNFD, but with some additional fields. In particular, the SDT field and the VCIP field, they are new, and they are belonging to the higher layer protocol configuration. We learned this from Ethernet. They can do so since I think mid of the 90s already. This was also not in the original protocol, that we can address virtual networks. Now we can do, and this is a real benefit, and we can run more complex systems and merge them together. I will show you an example later on. And we have two CRCs. You see the CRC1 and the CRC2. CRC1 is the preface protection, so we protect the preface of the frame. And then we have a second CRC, the frame protection. And now we protect also the first CRC. And this cascaded CRC, this makes it possible that we can achieve a handling distance of 6. And this was proved by independently by two German universities, academics. They are not engineers, they are from the mathematics departments, and they proved that this CRC is, or these both CRCs are capable to detect any 5 randomly distributed bit failures. So as I said, we have separated priority and addressing. When CAN was invented in 1986, there was not so powerful microcontrollers. And we should limit different fields as short as possible. And it's already 50% overhead in classical CAN. And this is why we have now not have had different fields was priority addressing. This was combined, so the IT field is used for addressing and for priority in CAN, classical CAN as well as KNFD, but in KNXL we have separated functions because we have more powerful microcontrollers and more powerful CAN controllers now available. And the 11-bit priority provides, gives the system designer the capability or the availability to have 2048 different priorities. You can assign them uniquely to each device. You can also assign several of these priorities to one device. This is the task of the system designer. This is independent of the acceptance field. The acceptance field gives you information what is the content of the frame or what is the address of the frame. You can use both, you can have both. You can have an address or you can have a content indication by means of these acceptance fields. The acceptance fields is also part of the 64-bit hardware acceptance filter. So you have the same possibility as in classical CAN and CAN-LD that you can hardware filter and you can reduce the interrupts to your host controller. So this is still possible and even more sophisticated. The service data unit type was invented to indicate what is, not only what is the content, but how I should interpret the content, depending on the higher layer protocol which I like to use. Of course, we can map multiple CAN, classical CAN frames and CAN-LD data frames into the 2048 byte, and that's indicated by a dedicated SDT value. But we also can map Ethernet frames. This means you can now use CAN-XL as a physical media for Ethernet frames. And you have the benefit of low price hardware, you have the benefit of very reliable and robust communication, and you don't have to suffer from the not so reliable communication in Ethernet, and particularly if this is very high speed. We can have also, of course, manufacturer-specific higher layer protocols. You know that the automotive industry is mainly using their own, each company is using their own higher layer protocol for the different purposes. They can also assign then the values for their solutions. We also can run TCP/IP protocol segments, though not just plain Ethernet frames. We have also CAN-Open and CAN-Open-CC and CAN-Open-FD transport and application layers. We can also have JN39 for those which may be commercial vehicles. And we have also then the possibility to assign an SDT for the 15765 transport layer, which is already used in diagnostic. And for further, we have still space to assign other SDTs to other protocols. This is important if we're talking about zonal in-vehicle network architectures. You know that it was mentioned in the morning that the cabling, reducing of cabling was nice. But still, we have in the moment in high-end cars multiple CAN networks, still a lot of cables. If we want to further reduce this, then we need the zonal architecture. Then you have zone controllers, maybe 4 or 1 or how many you like. And then you have a big backbone network there. Could be Ethernet based, 1 gigabit, 100 megabit, or even more. And you have sub-layered networks, still located at the front, close to the zone controllers. And now you have, you see here these colors, for example, purple, green, yellow, blue, and these are the logical connections. And how to do that without virtual networks? This is impossible. Now you design a virtual network, and you can use CAN-XL for that, or Ethernet. And now you can connect all the purple nodes, and they form a virtual network and can be run on the backbone network. So this makes the wiring much shorter, much less expensive and less challenging. This looks very abstract. I give you an example from the firefighting vehicles. You see here today's solution. We have in-vehicle networks in the truck by the OEM, and then we have a bodybuilder network that's called DIN4630, and could be a classical CAN network. And then we have for each of these body application units, we may have even sub-layered networks. This is a lot of wiring, because the one sensor is at the front of the truck, and the other one is at the end of the truck, and another one is in the middle of the truck. So we don't know where they are. This is a logical approach, but this doesn't help to reduce cabling. And if you now have, and you need a lot of gateways also in between, if you now have a backbone which is powerful enough to transport all the data, then you can just merge them, and you have one big a backbone network for the body application. You see, same structure, but now we can use one connection for multiple, and it doesn't matter if for example, this device and this device is located at the very same point. They use the same virtual network. This is, I think, a real benefit, in particular when you have larger vehicles or larger applications, and then you can use KNXL as a backbone network for that. Or you can use Ethernet, of course, that has the same similar functionality, or you use even Ethernet frames to be transmitted, for example, the cameras. One of the benefits of KNXL against other solutions is the physical layer scalability. So you know that other technologies, you can have jumps from 10 megabit to 100 megabit, but who needs 10 megabit? There are a lot of applications where you need less. You can use this with KNXL. You can even use the traditional high-speed transceiver limited to 1 megabit. Of course, then you have to wait, and if your application is slow, but you can benefit from KNXL capabilities regarding the higher layer protocols and all the other functions. You can also use KNFD transceivers capable to run 2 megabit in not optimized network topologies, or up to 5 megabit in using networks with 2 nodes. You can also use the CAN-SIG. We talked about this in the morning, the CAN signal improvement capability transceivers. These transceivers use still non-return to zero coding, but they allow, or they enable a speed of 8 megabit per second even in not optimized network topologies. And last but not least, if you have really speed requirements, then you can use the optional SIG XL dual mode transmission with PWM coding, pulse with modulation coding, and here we can run up to 20 megabits per second using hybrid topologies, and this can be also stars, double stars, and some other not optimized topologies. 20 megabit is the maximum. As Rainer has said in the morning, also that we can run with KNFD 15 megabit per second. Yes, we can do, but be careful if you have temperature range requirements from -40 to plus 150 degrees of Celsius. Then you can't run 20 megabit. Then we should limit ourselves to that what is appropriate. But under room temperatures, you will achieve 20 megabit per second. So all these transceivers which I have mentioned, they are able to operate in a non-return zero coded bit streams. So they can manage that. The arbitration bit rate is of those transceivers support bit rates between 40 kilobits per second plus and up to 1 megabit per second. That's also that one is standardized. You can go lower, but then you have EMC problems. In the data phase, bitrate new transceivers features improved symmetry parameters and SIG functionality to suppress the ringing. The CAN-SIG XL transceiver, they support optionally the PWM coding in the data phase. And the mode switching between the arbitration bitrate and the high speed up to 20 megabit, this is done in 2 steps in order to avoid EMC issues. You know that the automotive industry is very serious about EMC problems. And the bit rates I mentioned already, the database phenomenal is 61 for KNFD and 40 to 1 with KNXL. So what we can combine? Of course you can run a classical CAN with a standard KNFD. You can also use a CAN-SIG transceiver. This also fits. What you can't do is you can't run the CAN-SIG XL transceiver in fast mode because this is not supported by the classic CAN and CAN-FD microcontrollers. So microcontrollers can run with CAN-FD transceivers after 2 megabit, and in some topologies with 2 nodes only you can run up to 5 megabit per second. With SIG transceivers you achieve 8 megabit, even in multi-block applications. And the same is true, of course, for the CAN-XL protocol controllers. They also can use these two kind of transceivers. If you're using CAN-SIG-XL fast mode transceivers, you can run up to 20 megabit per second. And now the scalability has another benefit. You can combine a CAN-XL and CAN-FD and classical CAN communication. You can run this all on this very same network cable. However, you need then to configure 3 different bit timings. One bit timing for the arbitration. Let's assume 500 kilobit per second. And another one for the FD communication. Let's assume we have 2 megabit per second using standard FD transceivers. And we have then possibility to run up to 5 megabit. For example, if we are using the SIG transceivers with XL capability, so that we can use them, but we can't go into the fast mode because we are using the others in parallel. But still, you can use with a slower rate also CAN-XL and combine this as CAN-FD and classic CAN communication, all in one network. And this is a real benefit for many, many applications. The CAN-SIG-XL transceivers operate in 2 modes, as I said. They support non-return to 0 coding in the SIG mode, and in the optional pulse with modulation coding mode, they are all called fast mode, then they have another bit coding. When using the fast mode, error signaling needs to be switched off. So you will not have any error frames anymore on the network, on the data link layer. Of course, this means we have no data consistency combined on the data link layer. But you have to solve this then in the transport layer, for example, as Ethernet is doing it. And there you can now stop then the communication and can indicate that this information is wrong and can report an error. The arbitration bitrate, and this is also one of the limitations, is limited to, as I mentioned already, for the SIG transceivers for CAN-FD, is limited to a little bit more than 660 megabit per second. This means we are running 667 kilobit when using all priority IPs. There is a solution when we limit ourselves with the priority IP values that we can still run 1 megabit per second. But this is then a limitation, and we have some schema for that, how to do that. We don't recommend this, but if this is a need, you can do so. So in the database, we have another voltage level. And you see that the level 0, which represents the logic of 0, is just plus 1 volt instead of 2 volts, as you know it from the classical CAN transceivers. And the level 1, as the logical 1, is a minus 1 between the 2 lines. So in total, it's all, again, 2 volts. So there's no limitation or no disadvantage regarding the difference, voltage difference, but it's just between the lines, just 1 volt. In one case it is plus 1 volt, in other cases minus 1 volt. And this is how we can achieve the 20 megabit per second. But take some attention, the The cheaper bitrate is highly depending on the connectors and cables which you are choosing. So this has some impacts. And this should be, or it could be also come in mode shop, so we need to come up with some specifications CIA has not done yet, but we will do. So there will be new specifications for KNXL cables and connectors and come to mode shocks. We can use, not under all conditions, for 20 megabit per second, that what is already used for KNFD. Let's have a look to the status of the documents. As I have already reported, ISO DIS 1188-1, which is specifying a standardizing protocol. This is available, and we have integrated the CIA 610-1, which is the KNXL protocol, as well as the CIA 604-1, which is the KNFD Lite protocol. Both are now in the international standard, and you can purchase this draft international standard, and next week we will resolve the comments which we have received from the different countries. And the same is for ISO FDIS 1188-2, which describes the transceivers. There's the SIG transceiver, original specified in CIA 601-4, and the SIG XL transceiver, original specified in CIA 610-3. Both specifications are now included into the international standard, and there's a final vote. And in this final vote, there are no technical comments more allowed, just editorial ones. So this is quite stable, and I will report later also a little bit about the availability of the products. This shows you that for the chip makers, it's more easy than in the past. In the past, they had to consider multiple documents to make an implementation. Now they can do it very easily, and they can decide if they want to be compliant with the parameter set B, the parameter set C, or the parameter set A. A is the traditional one, B is the improved one, and then you have at the end SIG XL, which is parameter set C. We don't use the trade names, we use the parameter sets. And now they can go to all the tables, and they can now decide, I want to be compliant to this parameter set, or to this parameter set, or to this parameter set. And then they can make their products, implement them, and then you can see, okay, they comply to parameter set Z. This means they are compatible with the, they are compliant with the KNXL transceivers. CIA has submitted the protocol and the specification for the transceiver to ISO. What we will not do, we will not give all the specifications to the ISO, because some of them will change frequently. What is not changing frequently, that will be the conformance test plans. We are working on them, and when they are ready in the CIA, then we submit them for ISO to be integrated into the ISO 16845 series, so that the automotive industry is satisfied. They can make the conformance test for these KNXL protocol controllers and for SIG XL transceivers. The CIA 611 series will be in the hands of CIA. There we will specify the SDU types, which I have mentioned already, and we will have also multi-PDU specification, and this is all under development. The SDT type, the first protocol, the first specification has been released. CIA 612, this is important for those which are looking for guidelines, how to design things, and they are under development, and they will be also very soon released. I hope that will be happening next year, beginning of next year. CIA 613 series, this is a very important series. There will be a specified data links layer security, which is called also KNSEC, and we will also have these documents available by mid next year, I hope, so that then the companies can start to implement the KNSEC protocol into the can control those. We're also working on EMC evaluation, and this is under development. The specification CIA 120, also this will be submitted then to IEC, but because there is another standardization body who is responsible for these EMC standards. And very interesting is that we also will have a CIA 910 series. This is for simulation. You have seen that the physical designing of a physical layer is much more complicated. And you will not build up prototypes and try it again and again and again. You will first make a simulation of your K network. And therefore we need to standardize those model for that, so that different companies can implement it, and that the implementation can be used in parallel. And we will have then use cases with simulation model requirements. And then we will have the PMD, which is then the mechanical parts of the physical layer, like cables and connectors. Also, they will be modeled. And we also will have the performance test of such tools, which will appear on the market. This is heavily supported by Volkswagen, and we appreciate that a big company like Volkswagen spend the money to support that to the benefit of the entire KXL community. As I already mentioned, we evaluate also the EMC. This is done in close cooperation with some universities in Germany, and at the end, this will end in some, or we will have to meet some EU directives, and also this will be ended in the IEC 6.228-3 standard. And I hope this will be happening also at the end of next year, that we can integrate this. To summarize, we need migration paths from today's in-vehicle network architectures to zonal-oriented in-vehicle architectures. This is a need, and we have more and more complexity in the vehicles, then we need to do so. But we can't do this in one step. So we need a migration path. The migration path will be different for the different OEMs. So we need to run several protocols, historical ones, in parallel to forward, to route, and to gateway them. And all this is possible if you are using KXL. And we need to run, in addition to the normal communication, protocols for security, functional safety, high availability, meaning redundancy, time synchronization, etc. And all this can be achieved with KXL because we have all these applications in mind, how complex they are. What is the status of KXL? You see that several companies have already released some IP cores. Amazon from US, mainly for military markets. Bosch has also one digital core design. This is a small company in Poland. The Fraunhofer Institute in Germany. Quasar has also a prototype. And NXP has some IP core available, but only for internal purposes. So their microcontrollers will be based on that. Peak system is also for internal use and something under development. And the same is for Vector, for tools. They have also an IP core available for internal use only. So those which make chips can buy the IP cores, integrate them. They don't have to do it by themselves. For most of the users, it's more interesting which companies support microcontrollers with KXL. Infineon has something under development, and we expect that before the end of this year they will give some engineering samples to the market. NXP has already some pre-production samples available. We have tested them in some of our Blackfest. Renesas is under development, and perhaps they catch up and will have also something available early of next year. And STM microelectronics, they have also already some engineering samples available. The CAN 6XL transceivers are available, some engineering samples from Bosch, we have seen them. Infineon has a system-based chip prototype. NSP has already the second generation of engineering samples for standalone transceivers. And Texas Instruments has also standalone engineering samples shown in this summer. Which CAN XL board level products you can look for? Bosch has an evaluation board. This is available, you can buy it. CNS Group has one. Quasar has some interface boards under development. Peak System has also interface boards under development, mainly dongles. And Vector has its own interface board, but just for internal use for the Vector tools. Which tools are available? CNS Group provides a validation tool, and it's available by end of this year. I have not seen it yet, but I hope it will happen in December. Vector has development and test tool prototypes available, and also a protocol analyzer we saw from Vector. Oscilloscope manufacturers have also adapted CAN XL. So Keysight and Oda Schwab, they have prototypes. The product from Teledyne is already available, and Pico Technology is also have something under development. For those which are interested also in software for CAN XL, Bosch provides a network driver for emulation board, and this is under development. GitHub, and this is an open source approach, and Volkswagen has contributed the Linux proof of concept for CIA 630-3 XL frame fragmentation. Also, there's something in open source available. Vector provides an ultrasound protocol stack prototype, and Volkswagen also has a CAN XL support for Linux kernel version 6.1 and higher. So this gives you an idea. We are already in the stage of pre-developments, and we have first prototypes available. And we use these, when we need these prototypes, to make our plug tests. We have done the first plug test in July 2021. We have another one done in May 2022, and this year in 2023 in Nuremberg, as well as in April in the United States. And we tested a lot of things, and we tried to connect multiple nodes. And we will have a next plug test in May with the new arriving products from Infineon and from Renesas and maybe others. You see, this is how such a plug test looks like. Multiple people come together, plug together their devices or their prototypes, and then we test it to prove that they are interoperable. But this is not just, this is one of the plug tests. So this is one opportunity to test the devices. But there was also one of the truck makers who has proved the CAN XL concept. So they used their normal standardized bus system, or the bus, and they have had CAN FD nodes. 4 CAN FD nodes, and they provide an adapter to CAN XL. We terminated the bus. This was a real bus, and you see the group here was taking a ride on the bus, and we survived. So CAN XL is really working. In addition, then we have had 2 additional CAN XL nodes. We had a camera, an Ethernet camera, with a CAN XL adapter, communicating over the bus to a display. And the display was also connected via an Ethernet interface. And this was not sufficient for us. And then we stressed the communication. There was a bus load generator to increase the bus load to nearly 100%. This was 92%. And still communication was possible, and still we could drive the bus, and we can do braking, we can do gearing, all this was possible. And this was proving that this works. We had used a 500 kilobit arbitration bit rate, and Daimler Truck uses then in the database 14.5 megabit per second. This was not that bad. And we was all satisfied, and I think this project was running for 3 months. So after 3 months, they finished this proof of concept, and now we know, oh, it's working. On questions? Oh, you're tired. Oh yes, please. Okay. Oh, wait. She brings you a microphone.
Okay, one question. In your slide, you mentioned the time synchronization for this CAN XL. So as I know, and before there is a time trigger CAN. What's the difference?
Time synchronization is not time triggered. Time synchronization, this is between the nodes. So this is specified in CIA 603, so that you provide the time with an accuracy of 16 or 32-bit, and then you can give this time information to the other node, so that they can adjust their clocks, their local clocks. This is not time-triggered communication, so it's time synchronization. This means we synchronize our. I don't have a watch, but normally, if we want to meet, we need to synchronize before our clocks. Otherwise, we will never meet. So if my clock is a German time and your clock is a Chinese time, we will not meet. If we agree on 12 o'clock tomorrow, then we need to adjust our. This is time synchronization. This is different to time-triggered communication. You can also combine KNXL with TTCAN. This is possible.
Yeah.
Good.
After your explanation, I think CAN SL is the next generation CAN, right? So sometimes I compare to time trigger communication, for example, first ray, TTCAN. So, but
no, this is another application. So the time synchronization is needed in the automotive industry to synchronize the local times in different ECUs. The time-triggered communication is to synchronize the different nodes. This is two totally different applications.
Yeah. Okay, I see.
Thank you. Other questions? Okay, then let's go to the last part of my presentations. It's a little bit a tricky one, because this would fulfill, I think, more than one day if we go into all the details. It's, I was asked by the organizers to provide some information on the CAN and road vehicle diagnostics. To be honest, this is something like to go into the jungle. In the jungle there are tigers, there are snakes, there are a lot of different animals. And there's a lot of trees and a lot of plants, and how to go through that is very, very difficult. And even I'm working 30 years more than 30 years for CIA, I have not the entire picture, nobody has. But there are some books, and this book is Road Vehicles Diagnostic Communication, or this is the German version, and they are quite good to get an overview. I have read these books, and there's a new version under development by one of the authors, Peter Subke, and he's an expert he's coming from the company Softing, and he is a real expert. He has done a lot of diagnostics in 30 years. And I know him very well, and he asked me to double check his book, his new book, and I have done so. And now I have a little bit more information about this jungle, and I will share what I have understood and can give it half an hour to you. So the onboard diagnostic in passenger cars, the new trend is we're going the United Diagnostic Services. The United Diagnostic Services, they are standardized. The service and the protocols are standardized in the ISO 14229 series. This covers all kinds of integer networks. It is now a common solution if you're doing the diagnostic via CAN, via Ethernet, via LIN, via FlexRate. It doesn't matter, they use the same application. For CAN, this is standardized in part, where it is, in part 3. This is UDS on CAN. This is what I'm an expert. I'm not an expert in UDS on LIN or on Ethernet, so this is not my business. So if they doesn't fit into one single data frame, the UDS message, for example, if you download things or if you upload things, then you need to split the message into segments, and this is specified in the ISO 15765-2 Transport Network Layer Protocol. This is valuable for classical CAN as well as KFD, independent if this is somebody using or not. So the old elder solutions for Keyboard 2000, a KVP 2000, this is standardized in ISO 14230-3 and DUCAN. This is 15765-3, specifically for CAN. They are still available in elder cars, but not in the future. So they are outdated, so to say. Now let's have a look, and here you see the jungle. And if you like to follow me into the jungle, then you see there's a lot of different specifications and options which you have to implement CAN or UDS on CAN. There are transport protocols, and you have to look which kind of network you're using, and then you have to find that what is appropriate here. This is a little bit tricky, but those people who implement that in the cars, there are, I think, maximum 50 different gentlemen and women who are doing so, and they know all this. And also the counterpart, this is the diagnostic tool manufacturer. They also need to know a little bit about that. So, as I said, this is the overview and the picture of the jungle. We are going a little bit deeper than we see the transport protocol. The transport protocol is well known. It's standardized in ISO 15766-2. And here we have now, if we have a message which is larger than you can transport with CAN frames, classical CAN frames or KFD frames, then you have to segment this, and you do this by the first frame, flow control frame, then the consecutive frames, etc. But now you are wondering why this is called frame. A frame is something on the data link layer, and I told you this on the transport layer. The reason is they have misused the terms, as many people are doing. So just normally if you would agree and define that on the data link layer we are talking about frames, and on the transport layer we're talking about segments, then these so-called frames would be needed to name frame segments. First segment, flow control segment, and consecutive segment. All these standards which I have shown before, they don't use a harmonized terminology. This makes it hard to understand them. I'm fighting since 10 years to harmonize terminology over the different, and this is one organization. This is ISO. And now you can assume you have other organizations like CIA, like SAE, they use also different terms for the same thing. This is confusing, and young engineers, they need 2, 3, 4 years before they understand these standards. So this is a jungle of the diagnostic. And this is the only part which is highly standardized. but confusing standardized. So CIA tries to take the lead, and we hope that we can one day overcome this confusion of engineers. Besides the transport protocol, there's also a standard in this series, ISO 15765L5, which specifies the bit timing. This is needed that external tools and the gateway to the in-vehicle network can talk to each other. And we have specified their solution for classical CAN as well as for CAN-FD. And this shows you the 2 megabit, 4 megabit, and 5 megabit database bit timing standardization in ISO 15765-5. In the moment, I have not seen any of the OEMs supporting this. Though there was a wish to do so, what they don't provide this at the interface for the external tools. They have just implemented this for downloading software into the electronic control units. So this means they can do this in the factory, but afterwards they don't support this interface anymore. So it means the garages which are using the tools can't make benefit of it. So this is a trade-off. It is used by the OEMs from General Motors via Ford, the German car makers and the Japanese car makers, but only for their internal purposes. It's not available for the open diagnostic interface. There's also an emission-related diagnostic necessary. This is standardized in ISO 15031-5, and this is regulated by different authorities in Europe, in US, and other countries. I don't know what it's about Taiwan, but I think it's also here. You're using this standard, and this has to be supported by the different car makers to get permission to run the cars in those countries. The implementation of the worldwide harmonized onboard diagnostic, also known as WWH-OBD, between a road vehicle and external test equipment is standardized in ISO 27145 series. So this is that can the police or the garages or the authorities, the national ones, can test the vehicle on emission-related information, and so then you have access to them in a standardized way. So the ISO 27145-1 document provides general information, use case definitions. Part 2 defines the regulatory data elements which you have to support, and to provide an external, to provide this to an external test equipment with the diagnostic status on the onboard diagnostic system in the road vehicle. Part 3 is then defines the UDS services. You have heard about that UDS is that what is in the future only allowed and used, and the subset is necessary for the emission-related diagnostic, and that's also standardized here, so make just references. And then we have also the part 4, which specifies the OSI layer configurations for the classical CAN-based connection between vehicle and external test equipment. You can imagine that nobody is going at the moment to CAN-FD for that purpose, because all the garages are equipped with test equipment based on classic CAN, and they don't want to throw away their tools and buy new ones. The same is for the police cars. In the United States, all police cars are equipped with such an interface, and they can go directly to the connector of the car and can read the emission-related information. And CARB, which is in California, and they have denied it to go to CAN-FD or to any other interface. So they will stay for the next 10, 20 years with this standard based on classic CAN. So this is why we need, also in the future, even if we introduce CAN XL, still to support classic CAN, because otherwise you will not get this information out of the ECUs. And then we have part 6. This specifies the requirements for the external tools, with the test equipment, and this is important for all the tool makers, which are supplying the garages and might be also the OEMs. Besides this passenger car, we also have combustion vehicles for commercial purposes, and they use mainly the J1939 approach, which is a standardized higher layer protocol. In part 73, we have specified the diagnostic messages. As far as I know, they have at the moment 60 different diagnostic messages standardized. You see one for the bootloader or for extended travel code information. You have then also some of them which are emission related, etc. And this is supported also by tools. You see such a tool, and then you can read and interpret this. It's quite easy to do for the implementer of those tools. They just read the specification, and then they can interpret the received data from the ECUs. The format of such a messages looks always the same, it's standardized. So we have for the suspect parameter, which we are looking to. Then we have a low byte, and then we have a mid byte. This is 2 bytes, 60 bits. Then we have then also some information about the most significant SPN. This is the number indicating what is the content of byte 3 and 4. And we have then byte 5, also then in addition that we have there the failure mode identifier. And then we have in the last byte, then we have there the conversion mode, and we have the occurrence count. So then we can count how often this failure has been reported. And you see also the description for the FMIs. We have a high, low, most severe failure. We have a voltage above and below normal. We have abnormal update rate. We have abnormal rate of change, or whatever is out of calibration. There's a lot of information given to the user, and then you can repair the car, or you can replace the ECU if this is too dirty. Okay. This was the short trip through the jungle of diagnostic. And now we are back and we can have the last session, which is then questions and answers. And don't be shy. There are no stupid questions, only stupid answers. I hope I will not give stupid answers. Thank you. So I think we can have questions on all topics of today, and Rainer may assist me. Then, if this is coming to some things which I cannot answer, and we will look if there are questions from your side. You can have also the questions in Mandarin if you don't like to talk in English. Then the translator will translate this.
你好，我请教那个 Ryan， 就是刚刚介绍的 CIA 454，它包含的那个 Battery Pack 的 management 跟那个 DCAC 的一个 management， 那这些东西它实际上也包含在CIA 418跟419的一个。哦 ，OK， 哦 ，sorry。
Perhaps you can translate this. Yeah, you could repeat.
OK. 我想要请问的就是说，因为刚刚介绍的那个 CIA 454，它的那个 spec 里面它是包含了那个battery pack 的 management 跟那个 DCAC 的一个 FNG management。那这些东西它包含在那个 CIA 418跟419。 那我想要请教的问题就是说，第一，他们之间是否相容？第二，它是
Wait a moment, please. So if you speak and the translator speaks, I can't hear the English translation. So please have short questions.
Okay.
And then you are waiting, the translators are waiting until you finish, and then otherwise I have here Chinese and English and paragraphs at this time.
Sorry.
Okay.
No, I think I got it. So, as far as I understood, your question was whether CR454 or other CR specifications are compatible somehow to each other. And
yes.
Unfortunately, I have to admit that the CR454 is somehow independent. So, of course, we had a look to these specifications that we already had in Canon automation, but on the other hand, we had there already some input from some companies and also the other association that said we have already a plan how to put information interchange and distribution in light electric vehicles, and they submitted already an entire proposal, and we analyzed this proposal. We introduced also our learnings that we had already from these other specifications, and then we updated and generated the CR454. So it's independently in contrast to, or in regard to the already existing specifications like 418, 419. Nevertheless, you should already know or find all the relevant information maybe at another index in the object dictionary. Did this answer your question?
Yes. Another question,如果说像我们在做充电器跟电池，就是 Peter Pack， 那我们现在到底应该 follow 418、419还是454？
So this depends on your application field. So which customers are you addressing? So due to lack of time, I could not emphasize what exactly is a device profile, what exactly is an application profile. So if your customers say, we follow a 454 application and you like to contribute to that, then you should provide the 454. The more generic approach for a market which is not clear to you, maybe you're a manufacturer of charging units and you have no idea to whom you provide, then maybe the generic 453 could be more appropriate. But this depends, and at the end of the day, as we demand in 454 a software update capability, while the CAN interface, even so it's rather simple for you that you can say, okay, once the customer demanded, provide the right software update, and that's it.
So I can add maybe for the 418 and 419 specification. This was invented in the mid of the 90s for the forklift industry. And in the forklift industry in the United States, they use this, and also in other countries. There have been sold, I think, more than 1 million of those chargers. Batteries. You will not, you have to implement that because they will not change. So they don't need an energy management system because this is in the forklift. They just need to charge the battery. This is a point-to-point communication. That's what Rainer was saying with the 454. This is different. This is the energy management within a light electric vehicle. So this is two different approaches. The one is just have a communication between the charger, which is mounted on the wall, and you go with your forklift to there and charge it, or you have a field of batteries. There's also a non-mobile application. Then you have, let's say, 1,000 batteries and they want to charge them. Then you use the 418 and 419 specification. These are two different applications, and they are not in competition by this means, because the one is integrated in the vehicle, 454, like in an electrical e-bike or a pedaling, and the other one is external. So this is something completely different.
Okay, thank you. Very nice to meet you.
Are there more questions? I think we have provided also the email address. If you want to have something that's in the handbooks, you can write always email to us, please, in English language. Formerly we have had 2 Chinese employees, but they are gone. Unfortunately, so we don't have an engineer anymore with the deep skills in Chinese language. My Chinese is very limited. But you still can write, and I think most of you can write quite well in English, and can also read our response. Okay, looking around. Oh yes, please.
Since you give me a time, so I just one single question about, actually the previous one about the CAN-XL. Actually just mentioned about, it's just not a prototype, it's just about making the turnkey solution actually from like the Bosch or blah blah blah, like the Infinity and something else. I just want to know about the CAN-XL, the market, when it could be booming soon, or just standing for a couple of years after. I would like to say about, actually I'm from Yobotong, it's similar to like the Infinity and SDM something.
Yeah. So it normally takes some time, depending on your internal schedule of new microcontrollers. If you don't start now, you're too late. This is true. And we don't know, the automotive industry is, they need, or their supplier, their tier ones, they need, let's say, 2 to 3 years to develop ECUs. Okay. And then it depends on the OEMs when they introduce CAN-XL in their cars. So we don't know what are their plans. Volkswagen has a plan, perhaps, to go in the way of CAN-XL by the year of 2028, 2029. Normally they are delayed by 1 year. So 2030 is the proper time. If you want to have your microcontrollers compliant to CAN-XL and want to integrate such an IP core for CAN-XL, then you should start normally 5 years before. Because this is not just the CAN-XL that you want to integrate, you have a lot of different others here. And we are now in the year close to 2024, and we are still in the prototyping phase. You have seen that Infineon and Renesas are the next one, which will provide prototypes. And I would, even if you integrate an IP core, you need to test this on interoperability, because IP core is only half of the bill. The other bill is, the other half of the bill is that what you implement on additional functionality. So we don't know. The IP core provides just a CAN-XL controller. It's no memory, no filters, and we now should test your device in our backtest. I think this will be valuable for you to learn what is not functioning before you really have a volume production microcontroller. So that's my answer. So 2030 will be realistic. So I'm conservative. I'm old. I'm conservative.
Very clear answer for me, so I will take my opinion.
Okay.
Thank you.
Go ahead.
Maybe pass another one. Okay. So.
请问还有人要提问题吗？
So if there are no other questions, you have the opportunity to go in touch with us by means of email and also by the hosts here. I'd like to thank again for the organization. It was so perfect organized. I'm glad to be here. Thank you.
谢谢。好的，那今天的会议就到此结束哈。那待会收拾东西后，那跟着我们的
他们的引导到楼下搭游览车。那自行开车到会场的呢，回家路上也请您小心。